All right, so finally, I want to do just some silly examples of nuking mosquitoes, which is basically silly proofs using big guns for little problems. So just some fun and frivolity. Let's introduce one of the most difficult and celebrated results of 20th century mathematics. You quite possibly have heard of it. It is called Fermat's last theorem. And it says, for n at least 3, there are no integer solutions to the equation a to the n plus b to the n equals c to the n. So there is no cube that is the sum of two cubes, no fourth power that is the sum of two fourth powers, and so on, for any power at least 3. And this was an open problem for 350 years, since sometime in the 1600s even. It was solved finally in 95 using basically high-tech modern tools. Things like elliptic curves and the Galois representations and automorphic forms. Basically very high-tech number theory. Went into it, and here is a nice application to show just how worthwhile and useful this result is. So a theorem, the nth root of 2 is irrational for n at least 3. And the proof is by contradiction. So we'll start off the way we normally do in our familiar proofs of this kind of result. Suppose that the nth root of 2 can be written as p over q, or let me say r over s, for some integers r and s. Then taking nth powers, we get 2 equals r to the n over s to the n, or 2s to the n equals r to the n. And now, what can we say? Why? This means s to the n plus s to the n equals r to the n. And that's a contradiction, contradicting Fermat's last theorem. How wonderful. Unfortunately, Fermat's last theorem is not strong enough to prove that the square root of 2 is irrational. For that, you will need a different technique. Very nice. All right, let's do another example of this ridiculous kind of thing. Here's another serious hard theorem for you. There exists a discontinuous function from the real numbers to the real numbers. Not every function is continuous. A very deep and difficult theorem. But we have what it takes. Here we can give a proof of this fact. We can give a non-constructive cardinality proof. So the idea is, we've seen this kind of thing before, consider the set of functions from the real numbers to the real numbers, and let's think about the cardinality of this set. Well, we get at most that many functions by limiting the codomain. So we have this inequality. The number of functions from R to R is greater than or equal to the number of functions from R to 0, 1 in the sense of cardinality. And we've seen that this is in bijection with the power set of R. And by Cantor's theorem, well, Cantor's theorem essentially says that the power set always has strictly larger cardinality than the original set. So the set of functions from R to R is strictly greater than the cardinality of the real numbers. On the other hand, if we have a continuous function, we can recover it, can be recovered from its values on rational numbers. This is essentially because if it's continuous, then we can get approximations to the value of the function by taking approximations of the input, and the rational numbers are good enough to approximate any real number. Which is to say, equivalent, or so, which is to say, it can be recovered from its restriction from rational numbers to R. And what this tells us, that the set of continuous functions is at most as big as the set of functions from the rational numbers, the real numbers. And it takes a little bit of work, but you can show that this actually is equal to the cardinality of the real numbers. Basically, because the rational numbers are countable, they are not big enough to expand the size of the real numbers by taking functions like this. So, in the classic cardinality style that we have seen a number of times before, since the cardinality of all functions from real numbers to real numbers is strictly larger than the cardinality of continuous functions from R to R, we conclude there must exist a discontinuous real function. And that completes the proof, although since we used a non-constructive existence proof, we still have not found an example of a discontinuous real function. So there we have it, two silly little examples of proving some simple statements using machinery that is way overpowered for the job.